In this video, we contrast populations and samples. In a previous video, we looked at the process of starting with a substantive question, which we then formulate into a statistical question. We then collect and analyze data in order to determine our statistical conclusions, which we use to draw our overall substantive conclusion about what we learned and what we think it means in a more general sense. In one of our examples, we looked at class size and gain in math performances on the STAR assessment. But notice how the statistical question talks about 250 third grade students in Maine, but the substantive conclusion talks about larger math gains, much more generally, much more broadly. This illustrates the difference between a sample, the 250 students, and a population, all students or maybe all students in Maine. The population is the larger universe of individuals about which we want to make a conclusion. It's everyone we want to understand or describe or make inferences about in our study. Generally, we think of the population as a real thing. It might be all of the public high school students in a state or all of the registered voters across the country. Sometimes the population may be a little more theoretical, such as all of the possible outcomes that might occur or everyone who may receive an intervention. The key is that the population is everyone or everything about which we want to draw conclusions or make inferences. Parameters are characteristics of the larger population that we typically don't know. For example, the average number of hours per week college students spend studying. I don't know what that is. Probably no one does. At least probably no one knows exactly what that number is. And that's the case with populations. We generally don't know what the values of those population parameters are. We don't know the average number of hours all college students spend studying. Now, that said, there are times where we do know the value of the population parameter. For example, in our research, we often work with population data. For example, all of the birth records for a state. Because we have data on all the babies born in a state, we know the average birth weight in that state. We know that population parameter. But as a rule of thumb, we generally don't know these population values. They're things we're interested in, but just don't know. In contrast to the population, the sample is a subset of the population from which we do collect data. It's a subset of the population that we can access and measure and study in ways to learn more about what we think the overall population looks like. Consequently, we often use the sample to estimate those unknown characteristics or values in the larger population. Just like the parameters are characteristics of the population, statistics are characteristics of the sample. The difference is that unlike those population parameters that we generally do not know, we do know the values of the statistics in our sample because, well, they're right there in front of us. We can calculate them from our sample. Instead of the entire student body at UMaine, I can sample 40 students and collect information on how much they study each week. I can then calculate the mean for that sample. Maybe the mean for my sample is 20 hours each week. We know that value. Now, because we don't know the population values, the parameters, we often use the corresponding statistic based on our sample to estimate those unknown parameters in the population. For example, we may use the number of hours students in our sample study to estimate how many hours all students at the university study. To keep track of which is which, are we talking about a mean for a sample or the population mean, we use different symbols for each. This table jumps a little ahead of ourselves, but you can see how we label the same features in samples and populations differently. For example, we'll refer to the sample mean as X bar, while we refer to the population mean by mu. No, not that mu. I mean the Greek letter mu. There are other important things like the standard deviation, variance, and correlation that we will discuss in future videos, where we'll also have different symbols based on whether we're talking about the value for that characteristic in the sample or the value in the population. Now, don't worry about all those terms like variance and Greek symbols like mu. We'll introduce these in future videos. But the key point here is recognizing the connection between parameters and statistics. Parameters are the characteristics of that larger population that we generally don't know. Statistics are those characteristics of our sample that we do know because they're right there in front of us and we can calculate them. As I said, we're often using statistics based on our sample, X bar for the sample average, to estimate those unknown parameters in the population, like the population average mu. Because we use the sample statistics to estimate population parameters, it's important that the sample be as similar or representative of the population as possible. Ideally, we do that by randomly sampling from the population. If I sample 40 students at 10 o'clock at night in the library, I'll probably get a different value for the mean number of hours spent studying each week than if I sample 40 students at a frat party. And neither of these sample means will probably be very close to the population average, that parameter that I'm trying to estimate. Garbage in, garbage out. Okay? That summarizes our discussion of populations, parameters, samples, and statistics. Unless we somehow have data on everyone in the population, we use statistics we calculate from our samples to estimate those parameters in the population that we don't know. Okay? Bye for now.